Suppose that x is an eigenvector of A with eigenvalue lambda. What can we say then about the eigenvalues and eigenvectors of, say, a squared or a cubed, or if A is invertible, A inverse? Well, let's start by looking at A squared. By definition of eigenvalue, so by definition, we know that AX is lambda x. This is the definition of eigenvector and eigenvalue. Multiplying both sides by A on the left gives us A squared times x is equal to A times lambda x. Or in other words, by pulling out the lambda, this gives us lambda times AX. But we know what AX is. We know that from over here. It's lambda times x. So this is lambda squared x. So in other words, A squared times x is lambda squared times x. Similarly, A cubed times x is A times A squared x, which is A times lambda squared x, which is lambda, that's equal sign, lambda squared times AX, which is lambda cubed times x. So in other words, x is an eigenvector of A squared with eigenvalue lambda squared, and x is an eigenvector of A cubed with eigenvalue lambda cubed. I'm going to box this because that's important. Now what if A is invertible? If A is invertible, then lambda is not 0. This is by Tim. So A inverse times the equation AX equals lambda x becomes x equals lambda times A inverse x, which, because lambda is not 0, so this is because lambda is not 0, is the same as A inverse x equals lambda to the minus 1 times x. So therefore, x is an eigenvector of A inverse with eigenvalue lambda inverse. Again, I'm going to box that. We can summarize this and even generalize this to give the following theorem. If x is an eigenvector of A with eigenvalue lambda, then x is an eigenvector of A to the k with eigenvalue lambda to the k. And this holds for each integer k greater than or equal to 0. That's always true. And it also holds for each integer k less than 0 if, in addition, A is invertible. This result is actually useful computationally. For example, let's try and compute this thing here. We could go and multiply this matrix, which I'll call A, by itself 10 times, and then multiply by 5, 1, but that would take a lot of work. However, by finding the eigenspaces of A, we can show by what we did in the previous lesson that v1 equal to 1 minus 1 is an eigenvector for A with eigenvalue minus 1, and v2 equal to 1, 2 is an eigenvector with eigenvalue 2. Using techniques from earlier in the course, we can write 5, 1 as a linear combination of the vectors v1 and v2. In particular, we can figure out a way to write it as 3 times v1 plus 2 times v2. Then a to the 10th times 5, 1 is equal to a to the 10th times 3v1 plus 2v2, which is 3 times a to the 10th v1 plus 2 times a to the 10th v2, which is 3 times minus 1 to the 10 v1 plus 2 times 2 to the 10th power v2, which, plugging back in what we have for v1 and v2, is equal to 3 plus 2 to the 11th minus 3 plus 2 to the 12th. Now, it might not have seemed that great of an improvement when we're just raising to the 10th power. Box this. But say we're raising to the 100th power, to the millionth power. This is much quicker.